No? You think you never drink water? No.
All right, let's begin. So I have this story to tell you, as you know. So this is like it's a Christmas Eve service last year when I was out with my in-laws in California, and it was amazing. Like the placard out in front of the church said this, where we went for this service. I was like, I was like you are right now. I was like scratching my head. I was like, that's like the course I teach, that's the unit, and that's like one of the names of the units I do in this pre-calculus course I teach back in Maryland. I was like blown away. So I took this cell phone photo in like really even light.
Oh, and it was really pixelated.
I added like kind of some filters that made it look like it was generated. I added this thing down here that makes it look like I generated like this website, when in fact it's actually a real picture, right? Isn't that incredible?
Yeah, that was really smart.
I know, it's hard to believe, right? I know, we can't fool you anymore. Okay, we're going to start our unit on vectors. You have in front of you the traditional colored sheet. There are objectives on the front. There's some homework listed on the back. You're doing homework 1 tonight. And you, of course, have some dates for the calendar, okay? So we're going to talk about vectors today, and we should start by like just maybe asking if anyone is familiar with vectors. Now, I think the answer is yes, right? At the very, very least, you've heard the word vector. At the very most, you've like actually maybe even talked about and used vectors in a science class, especially a physics class, or in your POE class. Maybe you've done some free body diagrams, you've drawn some little directed line segments to illustrate some forces and things like that. So we're going to take kind of a mathematical angle. Math gives you the answers to everything else in life, so this will be good. Our goals today are to like tell you what a vector is, what it might be useful for in modeling the real world a little bit, but we'll go into that in more depth in the coming days. And also to do a couple vector operations. Can we do a couple things with vectors? Yeah, let's try and do it. Okay. So let's start by talking about what a vector is. One way, at least, of defining a vector is as an ordered pair of real numbers. There are lots of ways to write that ordered pair. One way your book likes, and we'll use lots of times, is with these angle brackets. And that is called component form. A comma B, or there might be more dimensions to the vector, but here's a two-dimensional vector, A comma B. A and B are each one of the components, right? That's why it's called component form. And right away we need to show you a picture, because like when we're talking about vectors, we're thinking about often thinking about pictures. The way we illustrate a vector is by a directed line segment. And maybe you missed what I just said. By a directed line segment, right? So I know that looks like, if you like were to sketch that and show it to a geometry student, they'd be like, oh, a ray. Okay, and I understand that it looks the same, but in the context of vectors, we're going to all understand that to mean it's not just the direction that matters, it's also the length that matters. Okay, so that I want the length to communicate something as well. Both the magnitude of that line and its direction matter. So in component form, it's just like, we're pointing to this coordinate A comma B or something. But it can also be given in component form, but it can also be given, like I kind of already hinted, as a magnitude and a direction. So you might record that information by talking about the length of this vector. That would be like the magnitude. And the angle, maybe how about the angle in standard position from the positive x-axis, measured counterclockwise, like we kind of normally do. That would be a good way to do it, though we'll mess you up and do it other ways too. But the point is, somehow by describing like a magnitude and a direction of some kind, that would also communicate the same good information. So for example, like if I was standing right here and I wanted to describe where the filing cabinet was in relationship to me, there are two ways I might do it and effectively communicate the same information. One way might be to be like, well, it's 15 feet that way and 15 feet that way. That'd be a great way to do it. Another good way to do it, though, would be like to say, well, it's 15 root 2 feet away from me at 45 degrees, right? Both communicate the exact same information about the whereabouts of my filing cabinet with relationship to me. Does that make sense? Okay. This is just stuck in here. There you go. The 0 vector has component 0, 0. Neat. Okay. Equal vectors. We should say when two vectors are equal. They're equal, they have the same components, or we've just talked about, or the same magnitude and direction. So that is to say, if I'm here, then maybe I give directions for like how you might get from me to Sue, right? And guess what? It's the same vector as it was a second ago that gave me the directions to the filing cabinet when I was standing here. So we consider those two vectors equal, right? It's the same set of directions, isn't it? Another way of considering two vectors equal would be, if you're thinking visually, would be up to a translation, right? If you can smoothly translate, that is rigid motion, translate, no rotation, just translate one on top of the other, then we consider them to be equal. So all I have to say, like, location doesn't matter, right? And that's partially like to capture this like idea in life that these vectors, like we want to talk about a velocity vector, we want to talk about a force vector, and we don't really care about its location necessarily, we just care about its magnitude direction. Okay, so after this slide, maybe you are starting to understand what a vector is, I hope. We'd like to talk about what you can do with them though too, right? So I'll hint at it and then we'll do more later in later in your life too. The first thing I guess we should stop to define also is what we mean by the word scalar. So a one-dimensional quantity of the type that you've often worked with like many times before in your life and in math class is called a scalar. So it's a one-dimensional thing. In particular, some examples of scalars include these things, not all of which you understand, but some of which you definitely do. For example, volume is a one-dimensional thing. Like if I wanted to tell you what the volume of my Nalgene bottle was, all I'd have to do is give you one number to report that information. Do you agree? And you would then know. Or if I wanted to tell you the area of your desktop, one number is all it would take to describe the area, or the length, or the temperature of this point right here in space at this particular time. One number is all it takes to describe the temperature of that point. And there are other more exotic things listed up there too. A vector is something that is more than one dimension in its quantity, in its measurement, right? So all of these things, I know some of them you might be like thinking, well, weight I can describe weight or force with one number, or velocity I can describe that with one number. Well, not in the technical sense. And maybe you've heard people already, let's actually hone in on velocity versus speed, actually, right? Because maybe you've heard people nitpick about that before. Have you feel like, well, speed is not the same thing as velocity. Well, let's nitpick for a second, and I promise if you haven't heard someone nitpick about that before, this is not the last time you will hear someone nitpick about that, okay? It'll happen again in physics lots, and in calculus we like to make a distinction too. Speed is the magnitude of velocity. Velocity is a vector quantity that describes not just how fast you're going, but the direction in which you're going also, right? So that's what we technically mean by velocity, even if, like, person on the street makes no difference. In, like, math and physics world, we definitely make a difference. When someone says velocity, we want to know not just how fast they're going, but in what direction they're going. Speed is just that, how fast you're going information. Yeah.
So when you do like a weather report and it's like the wind is blowing 10 miles an hour southeast.
That's a velocity. That is technically a velocity now, right? Because they told you both pieces of information. Absolutely. Yeah.
So then why isn't weight
So weight is another word for force. Force and weight are the same thing. Weight is like a fancy word for force. It's just we use it so much. We use it so much that like you're used to the direction down, right? So we stop saying it maybe. So you stop thinking about the direction which the weight is applied, but weight is technically force. Yeah. Mass might be maybe something you're thinking of. Mass is a one-dimensional thing, right? That doesn't change. But when we accelerate a mass, we get force. And it matters which direction we're going in. And of course, we should really refer to this really technical description. And by the way, I asked you to look at this PowerPoint, so maybe you already clicked on this link, did you?
Yeah.
All right, don't ruin it for everyone else. This is the multimedia portion of today's lesson.
Oh, so funny. No, I saw the thing before. It was like the villain from.
This is where you're going to get the real technical explanation. What does that mean?
I'm applying for a new film loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new weapon. Piranha gun! Oh yes! Fires live piranhas. Ever seen one before? Now you have my invention. Do you want a demonstration? Oh, ow! It's so difficult sometimes to get around that side.
There you go. So if you didn't know what a vector was before, I mean, you definitely did now. You do now. What movie is that from? It's so exciting. Okay. All right. Let's do some more vector work here. The first thing I might want to highlight is this kind of it's kind of cute, really. Head minus tail rule. So I mean, we kind of talk about vectors in the abstract, but how would we actually like think about one between 2 points in space instead of like in the abstract, Mr. Chase and the file gatherer, Mr. Chase and Sue? Like how would we actually create a vector between 2 points? Well, say I give you 2 points, then we might write a vector from A to B, from point A to point B, with this arrow notation above, where the order A, B, with the arrow over top matters. Like that would be different than BA. The direction matters. Well, that would be the head, that is like the arrowhead, minus the tail. So you take point B and subtract point A. And you get the component form of the vector AB. Does that make sense? I mean, I think you probably would have done that even if I didn't tell you the head minus tail rule, right? You're thinking like, okay, from here, this point to this point, how would you compute the component form of a vector from this point to this point? Well, somehow I need to measure this distance from here to here. Well, that's the difference of the x-coordinates, isn't it? And how would I measure this distance from here to here? Well, it's the difference of the y-coordinates. And furthermore, I didn't actually tell you that the coordinate system looks like this. But does that matter? It doesn't, right? Still, this point, coordinates of this point minus the coordinates of this point. Head, as in arrowhead, minus tail. Okay? Regardless of where the points are located, that's how you'll do it. It's just the offset in both directions, the kind of the net change in x and the net change in y. Okay, so now let's turn our attention to this problem if we're ready. So let's find first, before we do anything else and read the question any further, let's find the components form of this vector rs. I've given you 2 points r and s. Can you write down, maybe without even showing any work, maybe we can just write down the component form of rs. Careful, we're building a vector from r to s. So we're doing what? S minus r, right? Yeah, so what is it? 20, negative 10. Okay, now that we've passed that hurdle, check. We did the first part of the question. Now we have a little bit more of an interesting challenge here. Find a point Q so that RS, this vector we have here, and PQ are equivalent. Okay, we have this point P over here as well. What's Q? Well, we don't know. It's something that I don't know, comma, something else that I don't know. Whenever we have something unknown, we like to name it sometimes, so let's give it some names. What letters would you like? What did you say? I and Z. I see where you're going with that. Okay. Yeah, X and Y are good. A and B are good. I and Z. You can do I and Z back there. Okay. Whatever. The components are unknown to us. We'll call them X and Y, maybe. Whatever. Can you give me a component form for PQ, the vector from P to Q? So I guess I should have. We're using parentheses, I guess. What would that be? PQ is. What? Head minus tail. Right, what is it? Yeah.
Oh.
What would it be? X minus 3 and y minus 4. And then we're also told that they're equivalent. That this 20 comma negative 10 is the same thing as x minus 3 comma y minus 4. That should be enough information for you to tell me what x and y are. And then once we know that, we'll be done, right? So if x minus 3 is also known as 20, then what must x be? And if y minus 4 is also known as negative 10, then I think we're done. And then let's I think that we're done with this problem. But let's just like make sure this checks with our intuition. Let's all kind of draw RS in our minds. The vector RS is the vector from the point negative 20, 10, that's over here in the second quadrant, to the point 0, 0. That's a little weird. It's like a vector pointing to the origin. But we're saying, when we say this, we're saying we can translate it down, put it at the origin, and that this is the vector. Yes? The same vector. Okay. And now we're also making the claim, now that we found Q, we're also making the claim that that's the same exact vector by translation as the vector from 3, 4 in the first quadrant to 23 comma negative 6 in the fourth quadrant. Is that believable? I mean, we don't need to do the calculations again, but do those all seem right? Okay, yeah, Jeremy and then Isabel.
The triangle braces things.
Yeah, we can be a little loose about it. It doesn't really matter at all. But yeah, technically we use vectors, but sometimes the reason that we have a little bit of an issue is that eventually we kind of like stop thinking about points and vectors as being different things. So if someone says like Q equals 23 negative 6, well that's the point Q. Well, if you put in angle braces, then it's the vector to that point. We might call it the position vector of Q. Neat. I don't know. So I don't know. We can be a little sloppy, and that's like also okay with us. But technically, like I know early on you're like, wait, what's a vector and what's I mean technically this should be like maybe angle brackets or something. If you like that. Isabel, are you good? Or?
Yeah. My question was if there's really like if you didn't have like the coordinates for R and S, if you had one like component, does that always originate in the order?
I mean, it wouldn't really make sense otherwise. You might say we want the vector OR if you're coming from the origin or something where O is the origin. I mean, I don't know. Yeah, someone should ask the question better if you're having that issue. Oh, wait, before I put this, I almost slipped. You didn't see that, did you? Right. So before I tell you what the magnitude and direction, it would be a crime to like not ask you to tell me, right? Because you already know how to find. If I gave you the component form of a vector, I got the vector 2, 5 or something like that. Do you think you could come up with the length of that vector? I think you could, even if I didn't tell you how. So, how would you do it? Yeah, someone says distance formula, someone says Pythagorean theorem. We all recognize that these are actually all the same thing, right? Right, you could like think about the fact that there's like a triangle here. 2, 5. Find that length using Pythagorean theorem. What about the angle? Could we come up with the angle? If someone gave you component information, you could get the length. Could you also get the angle somehow? Yeah, maybe cosine or sine or whatever. But here's some trig. Absolutely, right? Trig gets you all the way home with this stuff, right? So I know you're like thinking, I thought trig was done. It's not done. It's always with you forever and ever and ever and ever and ever and ever. All right. So this is exactly what you just said. We're going to call it the magnitude, right, instead of the length. And magnitude is maybe a good name for it because length makes me think like a certain distance. But keep in mind that a lot of the applications we're going to look at are like a force or a velocity. And then maybe we want to think about magnitude. It seems strange, like what's the magnitude of the force? That sounds good. But if you say like what's the length of that force? That sounds weird, right? So that's why magnitude is maybe a better word for this than length. And then the angle can be found using techniques we've already talked about in trig stuff, right? If you know the cosine and the sine of the angle, you should be able to figure it out. Possibly using your calculator, possibly using like a really well-chosen trig function, trig inverse function on your calculator, or using, you should like think about which quadrant it's in, all that kind of stuff. So let's go ahead and try that with 4, -8. Tell me what the magnitude and direction are. you might need a calculator. By the way, what symbol are we using for magnitude? Do you see that over there? Yeah, that's a notation that seems like, hey, we're ripping that off of something else. But the absolute value bars maybe are actually a good thing to think about here, right? Because like back when you did the absolute value of a single number, maybe your teacher even told you like, well, the absolute value of a number is like the distance from zero, right? Or the magnitude of the number. It's like -10 and +10 both have a distance away from 0 of 10, right? So that, do you see why that like makes good sense here too? So we're going to use the same notation whether we're dealing with a one-dimensional quantity or a two-dimensional quantity or later a three-dimensional quantity. Can you even verify that the following formula works? Like if you want to find the magnitude of the number -3, does it work to use this formula? Does that give you, does it work for one-dimensional things too?
Yep.
It actually does. So what we've done is stumbled upon, like, you might be like thinking, well, hey, no, we ripped that notation off. Actually, I think the ripping off went the other way, right? Like this is the bigger, more general, beautiful idea, is this magnitude idea, okay? All right, with that being said, what is the magnitude of this guy? What does it come out to be? Square root of something. What is it? 80, 64, and 16. 4√5. Root 80 is good too, but whatever. Okay. So we did it. We got the magnitude. Check. And how are we doing on the direction out there? It's definitely which quadrant? I definitely need an angle in 4, -8. So we're over here. I'm going to draw a little picture because I think it will help for me. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. So we're talking about this vector, which we've just determined the length of that is 4√5. And now we're interested in figuring out what is this angle? Theta, we'll call it, I guess. What is that angle? How'd you find it? People who are finding it. You. You found it, didn't you? No, you have a calculator in front of you. You know what to do? Someone? What are they calculating? People in the back over there have calculators. What'd you find? In radians, degrees, whatever. No, it's got it. Negative. I'm feeling like that's too big. What did you say? Negative 1.8? 1.1. Oh, that might be right. I don't know. Is that what you got? I don't know. Negative 0.46. Give me that. Okay. Sign in. No, what do we want? What are we doing? What are we typing in?
Oh.
Yeah, what are you typing in? People who are typing things in. It's definitely got to be in the fourth quadrant in the end of the day.
So it's gotta be 300.
So what'd you type in? That got you some success here.
Sin -1 of. I said sin -1 of -8 over 4√5.
Yeah, so sine inverse of -8 over 4√5. Is that what you did say? It said 2, Noah? Okay, that'll get it for you right away. It's approximately negative in degrees, -63 point what?
4.
Or degrees. Okay, if someone did it in radians, that's fine. Whatever. Anything correct is good, right? Yeah. Not particularly on this one, right? I could give you a problem that was a nice angle that you knew though, and then you could do it, right? But yeah.
Is there any reason why we can't do arctangent?
Arctangent's beautiful here, right? Because it just I do arctangent of -2, right? That's a nice one. You don't even have to compute. Well, we already found the magnitude, so this is not hard either. So whatever. Do whatever you want to do. Just again, get the right answer, so you're good. The only thing we want to caution you about is inverse cosine, because what will that give you? It'll be the inverse cosine of 4 over 4 root 5, and that'll give you back first quadrant angle, and that's fine, provided you know that it's not that and you need to adjust it, right? So, anyway, we're good. Yeah, question?
Wait, does the magnitude of a vector have units?
Not on this particular example, but in general it will, yeah. Like, if we're finding some force vector, it'll have units of like newtons or pounds or something. If we're like velocity, it'll be in meters per second or whatever. All right, what about magnitude and direction? What if we're given magnitude and direction? This is maybe the easier direction. Can we get the component form? Can we go the other direction? Well, again, like the entire story is trig again. So with this picture, suppose that we know all the red stuff. We know the magnitude of v, the length of that segment, and we know theta, the angle in standard position. How would we find the length of this blue side, for instance? That's the x component, right? The horizontal component. How would we get that?
Say that trig sine or cosine theta is equal to.
If cosine theta equals, say it.
Is equal to the side that you want over the magnitude.
So the side I want is equal to.
The magnitude times sine theta or cosine theta.
Yeah, exactly. Did you catch what Ted just said?
Yeah.
Say it again. Yeah.
The magnitude times either sine or cosine theta will be equal to the components that you want.
Okay, well that's what I said. But say what you said first.
You take the magnitude, or no, you take one of your trig functions and you say that it's equal to either the magnitude to the side that you want over the magnitude. Like back in the beginning of trig where we said sine theta is equal to y over r and plus theta is equal to x over r.
Right, comes right from solving this out from the definitions of the trig functions. In particular, so the coordinates are magnitude of v cosine theta, comma, magnitude of v cosine theta. That's the component form. Done. Go home, right? It's like, yay. But let's just stop and appreciate this, that this is something we had thought about before, isn't it? In particular, what if the length of our vector, what if the magnitude of our vector is 1? Then what are the coordinates then? What? It's just cosine theta comma sine theta, right? Well, that's because our vector points to a point that lies on the unit circle, right? So, all right, this is one that doesn't require a calculator, I think, because 120 is like a nice angle. So let's do this one too. This time we're like asking you to come up with the components of this vector where I've given you the magnitude and the direction. Sue. On the what? On the previous slide or something? Yeah. Denoted just means like that's how we say it. Was that the magnitude? Yeah, so the magnitude we denote means like we represent using absolute value bars is what you would call them, using vertical bars on either side. Yeah, that's what we mean by magnitude. Yeah. Sweet, you learned a new word too. Extra points. Okay. So what is it? 52 cosine 120, comma 52 sine 120, right? We all know the cosine and sine of 120, so I think we'll be good. 52 cosine 120, comma 52 sine 120. What is the cosine of that? How about negative 1/2? And what's the sine of 120? Positive root 3 over 2, I hear you all say. Good job. Okay. So what is that? Negative 26, comma 26 root 3 would be a good way to write this vector. There it is in component form. Good job. Okay. Sorry. Was that good? Is that good? I mean, the reason I'm kind of rushing a little bit through this is because, like, it's new notation, new context, but the trig is all like, whew. Yeah, I got this. The trig should not, hopefully the trig is all stuff that is old hat, just in a new context. How are we doing? All right. Whoa, whoa, whoa. Yeah, we're using angle brackets to indicate that this is a vector quantity, but I really don't care if you use regular parentheses too. Either one. It did ask for a vector here, so trying to emphasize that that is what this is. Okay, come back together, please. We're not done yet. We've got. Oh wait, you still need this?
Yeah.
Show them you good too.
Like 10 more seconds.
What do you need? 10. That's generous. If we have 10 seconds. Okay. All right. Let's talk about vector addition and scalar multiplication. Two things we can do with vectors. I promised that we wouldn't just like talk about vectors, but also things maybe we can do with them. So let's start talking about first adding two vectors. Can we take a vector and another vector and add them together? The answer is yes, and the answer happens in exactly the way you would predict even if I didn't tell you. And that's, you take the components of one and the components of the other, and you add them component-wise, right? Exactly how you expect. Take that horizontal component of the two vectors and add them together. Take the vertical component of the two and add them together. And there you go. So that's not super interesting, and like I said, you would have probably expected that. But the thing I want to maybe slow down and say is, like, what have we actually done? And does it make sense? So let's think visually on this for a second. Here's the vector u and the vector v. And I claim that when we add them, it's like we put them head to tail like this. And the thing we get, the new vector, u plus v, is this one right here. Okay, now can we convince ourselves that that's actually the interpretation? Let's see if we can. I'm going to lay a coordinate system on top of this. Notice there's one absent, so I need one. Okay, so how about, here's the x-axis. And here's the y-axis. Okay? I just felt like putting them there, just for fun. Okay. Doesn't matter. The point will stand, no matter how we do this. Okay, so that was maybe a poor choice just because of how this is going to work. But the x component of the u vector, would you agree that this is the x component, or the horizontal, quote-unquote, component of vector u? And the horizontal component of the green vector, vector v, is this piece here. Just this piece from here to here. Do you agree that that's the x component? I just decided to put the x-axis here and the y-axis here. Do what you like, though, on your own paper. All right, is it clear to you, then, that the red vector has as its horizontal component, or its x component, the sum of the two? The overall sum of both the horizontal component from u and the horizontal component from v? And the same argument could be applied along the y-axis, right? Add these two together to get the overall component, y component for u plus v. All right. I mean, we went a little bit crazy there, but do you get the point that these definitely visually make sense too? That by putting these end to end. One more question there too. What's v plus u? Do we get the same picture? Do we get the same result? Like maybe if we put v and then u at the end of that, would that work? There's u, there's v, and there's u. Now we've got a picture of v plus u, and do we get the same picture in the end? Yeah, the resultant vector, the sum of the two vectors, is in the end the same picture, showing that vector addition is commutative, right? Vector u plus vector v is the same as vector v plus vector u. We get the same picture. You could do the same analysis we just did. And it is, what is the shape? Yeah, it's worth noting that this is a parallelogram, and that the red vector, u plus v, is a diagonal of that parallelogram. What about u minus v? U minus v might look like this. I guess you have to go now. I love you all. Bye. You'll be fine. You already looked at my PowerPoint, didn't you? Already. Over break. And I think you'll be pretty well suited for homework 1, even though we didn't get to the last slide. So we'll clean up a little bit tomorrow. We'll have lots of fun with vectors in the coming days.